Welcome. Everyone familiar with vibration analysis will know that low-speed applications and vibration monitoring are not a very easy combination. Well, on top of that, if we want to perform wireless vibration monitoring on low-speed applications, we see that is even more challenging. Well, in this presentation, I will try to show you that impossible is not a synonym for challenging. So the example we're talking about here are the monitoring of bearing conditions on overhead crane wheels. Monitoring bearing defects on overhead crane wheels are even more difficult than standard low-speed applications because we have a lot of background noise that is actually caused by the contact of the wheels of these overhead cranes with the rails. So the presentation here is split in three parts. In the first part, I will explain you how we performed the first tests that actually gave us the opportunity to look at which type of standards or which type of measurements allowed us to perform this monitoring. In the second phase, we actually performed that monitoring based on portable vibration, and in the last phase, we converted that approach to wireless monitoring. So the first tests date back from 2013, where we provided some first measurements on these overhead cranes to see if it was actually possible to provide bearing monitoring on this type of applications. So to do this, we positioned accelerometers close to the bearings of the overhead cranes, and the analysts themselves with long cables positioned themselves on the crane itself, where they could be in a safe location while the crane was moving. When we perform this type of measurements, we see that standard vibration measurements will not give us very good results. The only thing that we will see is a lot of noise, and it doesn't tell us anything about the condition of the bearings itself. So for that reason, we need to use some more advanced techniques based on specific types of filtering and then very high frequency sampling. This high frequency sampling will allow us to detect stress waves that are caused by the bearing defect and that are much higher in vibration frequency than what is resulting from the background noise. So this is an example of some of these first measurements where we compare the standard reading on the bottom with three different of these high frequency sampling techniques, each time with a different filter. When we remove the measurement on the bottom, which clearly only gives us some noise that has no relation to the condition of the bearing, we end up with this picture. And we see here that applying different types of filter, one specific filter allows us to get a very clear image of the pattern that corresponds to a specific bearing defect on this crane. When we compare this measurement to the other measurements using the same technique, but on the bearings close to the defective one on the crane, we actually see that the difference in amplitude clearly indicates us which of the bearings is potentially the one that has a defect. Doing the analysis a bit more in detail, we actually see that the pattern that we see is rather standard if you're familiar with vibration analysis, and it clearly corresponds to an outer race defect of the SKF 23240 bearing that's installed on the portal crane. The amplitudes were very low, and because this was the first time we performed measurements on this type of application, it was very hard to predict whether the defect would actually already be rather severe or if it would only be a very small beginning defect. So for that reason, it was recommended to replace the bearing, inspect the bearing, and see further how we could develop a monitoring program based on this. Well, when we inspected the bearing, we actually saw that even with these very low amplitudes that we detected, the bearing defect itself was already very severe. But it clearly proved that it was possible to detect this type of defects based on these portable measurements. So that leads us to the next phase, where we actually started to provide condition monitoring based on the portable data collection. So based on the results of the first campaign, we set up a complete monitoring program for a total of 70 overhead cranes, which in total corresponds to approximately 1,500 bearings. If we take a look at the results of this monitoring program, this is how it looks like. So in red, it is indicated how many bearings actually failed unexpectedly over the period 2009 to 2016. And then the bearings in green are the ones where we actually recommended to replace a bearing before it actually crashed. So in total, 45 bearings were replaced between 2014 and 2016. Each of these was inspected very thoroughly to see how severe the defect already was, to be able to perform an even more reliable detection afterwards and a more reliable analysis? Well, we actually saw that out of the 45 bearings that we replaced, approximately 30 displayed severe defects as the ones shown on the picture on the right side, where we can really say that the replacement of the bearing was really justified. On approximately 15 or 16 bearings, we actually saw that the defect was visible, but actually in a very early stage, and where you could say, okay, there is something that we see on the bearing, but we consider that this is too early to perform a replacement, and we should have continued to monitor that type of bearing. So based on this, it was possible to fine-tune our analysis and to get even better results in the years after. So we can conclude that based on that experience, we were actually able to provide a monitoring program which works quite reliable for these overhead cranes. But there is something, however. If we take a look at this type of measurements, there are some disadvantages as well. First of all, when we look at how long it takes to perform these measurements, we see that in average for one crane it takes us about 20 man-hours to perform the measurements and the analysis, which is of course a rather costly approach. Apart from that, we see that for a lot of cranes it is only possible to provide these measurements where these cranes are out of production, again causing additional cost for this monitoring technique. And then the last one, of course, that because we need to perform these measurements with our analysts on the crane while they're moving, we need to take special safety measures. So because of those three reasons, we actually considered if it was possible to perform measurements based on online monitoring, and more specifically wireless online monitoring. So that is the investigation that we started in 2018 to see which online monitoring systems would be suitable to use in this type of application. Because compared to many other applications, we see that actually having online monitoring in this application is rather difficult because of several reasons. First of all, we need this high frequency sampling technique, which is not readily available on many online systems. Apart from that, if you want to have a reliable measurement that is useful for bearing condition, we need to have a measurement while the crane is at least running at a stable speed for approximately 20 seconds. While in normal operation, the operation conditions are really very erratic. So only a couple of times per day, or even once every couple of days, this occasion happens during normal production. And then the third one, of course, is that the system would allow wireless data transmission to limit cabling costs and to improve also the reliability of the system. So the system that we chose to provide these monitoring techniques is the system that was developed internally at iCare, which is the WeCare 200 wireless system. So that is a system which indeed provides the high-speed sampling techniques. It also allows to perform data capturing on external triggers, which allows us to take only measurements when the crane is in a condition where it's suitable to provide the measurements. And third, it provides local power supply, which is necessary for the continuous operation of the online system. So with the tests performed with this online monitoring system, we were actually able to detect that we got similar results as what we were possible or obtaining already before with the portable measurements. So this spectrum, for instance, clearly shows again the pattern of an outer race defect which was present and detected on the first bearing where we installed this test for the online monitoring system. So the online monitoring system is set up in the following way. So the sensors are connected to the WeCare 200 systems, which are installed quite close to the wheel bearings. Every WeCare 200 system accepts 4 of these accelerometers. From there on, we have wireless transmission to the gateways, and the gateway itself will connect or to the cloud through 4G, or will have a direct connection to the corporate network of the customer. So both options are possible. And both the gateway and the WeCare 200 modules have local power, which is of course necessary for an online monitoring system. So this is how the system looks like in practice. On the right side you see the large overhead crane. In the middle we see the cabinet where the WeCare 200 modules are positioned that are connected to the accelerometers positioned on the sensors. And then on the left side you actually see the inside of the cabinet showing all the WeCare 200 systems and the local power supplies. So as a conclusion, we can say that these wireless 200 systems allowed us to increase the reliability of the crane monitoring program even further, while eliminating some of the most important disadvantages of the system that was already quite successful as well, but as explained, rather costly and requiring a lot of special measures for the safety. Thanks a lot.